Alright, so today we're going to talk about the midpoint and the trapezoidal Riemann sums. So, the first question says approximate the area bounded by the graph of f of x equals x squared on the interval from 0 to 4 using the midpoint rule with 4 rectangles. Okay, so if we are graphing, let's get a sketch of this graph. It will be from 0 to 4, so 0 squared is 0, 4 squared is 16. So when we graph this, we need to draw a pretty tall graph here. 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, oh no, 13, 14, 15. Is that enough? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Alright, not the best graph I've ever drawn. But if we're graphing x squared, then 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared would be 9, and then 4 squared would be 16. And so for a midpoint rule, rather than using one of the endpoints, you're trying to pick the point halfway between. So on this particular graph, that would be at 0.5. It would also be at 1.5, 2.5, and 3.5. So rather than using either one of those endpoints, we would just use that point halfway between. And this had 4 rectangles. Thankfully, it went up 1, 2, 3, 4, so it makes a pretty simple division there. And so we would be taking that point on the graph here and drawing a rectangle. And then the point on the graph here and drawing rectangle. This one would be about right here. And then this one about here. Okay, midpoint is better than left or right most of the time because you're going to have a little extra over here, a little missing over here, and it sort of makes up for each other. For this one, we would just have the width of each rectangle. What is the width of each rectangle? Is 1. A lot of times students will use 0.5 because that's the number you're plugging in, but it's 1 because you're looking from 0 to 1 as this first rectangle. So the width of each rectangle is 1, and then you would just do f of 0.5 plus f of 1.5 plus f of 2.5 plus f of 3.5. And so let's use our calculator, even though, I don't know, actually I'm going to use my calculator, but I'm not going to put this into y1 just because it's too easy. Because all our formula is just x squared. So 1 times, and then it would just be 0.5 squared plus 1.5 squared plus 2.5 squared plus 3.5 squared. And so we end up with 21 whenever we plug that in. Let's see. I do know how to do this exactly because I know things I haven't taught you yet. The actual answer for that, let me see real quick. The The actual answer is 21.3 repeating. It gives you a pretty close approximation right here for this problem. So midpoint is a lot better than using left or right. Now, the rule is up here. Although I don't really use the rule all that much. I usually just think through these kind of logically. Think of drawing my rectangles. Think of what the width times the height is for each one. But this would be f of the midpoint of your two intervals. So like the xi would be 0, and then the xi minus 1 would be 1. Or then the next one would be 1 to 2, and then 2 to 3, and then 3 to 4 for that. So it's add them together, divide by 2, which this one was very simple. That halfway point was easy to find. If you had something odd, it might be difficult to do. Most of the time, they don't give that to you. Usually it's something fairly simple, a 0.5, a 0.25, something you can find fairly easily. And then this delta x right here, that is your change in x. It's also the width of each rectangle. So basically, width of each rectangle times f of that midpoint, which is the height of the rectangle. Okay, questions? All right, let's look at the next one. Example 2, ask you to approximate the area bounded by the graph of f of x equals sine x between x equals 0 and x equals pi. Use the trapezoidal rule with 6 subintervals. And this is calculator active. If we think of sine x, we're going from 0 to pi. Let's sketch a graph to help us out here. I'm going to go ahead and put 1, 2, 3, 4, 5, 6. This will be pi right here. I put 6 tick marks because they told me that we have 6 subintervals. And for sine of 0 is going to be 0. And sine of pi over 2, so the halfway point right here, it's going to be 1. And then sine of pi is back to 0. So it looks something like this. So if we split this into 6 subintervals, we're going to take pi, because that's the length of this interval, and we would divide it by 6. So that means this first little tick mark here would be pi over 6. The next one would be 2 pi over 6. But what does 2 pi over 6 reduce to? Pi over 3. Then we'd have 3 pi over 6, but that reduces to pi over 2. We'd have 4 pi over 6, but that reduces to 2 pi over 3. Then we'd have 5 pi over 6, which does not reduce. And then 6 pi over 6, which is pi. So we are supposed to use trapezoids. So that would mean if we take all these points right here, we would end up with something that looks like this. And our first subinterval and our second and our last subinterval, they're actually triangles. But just for some consistency, I'm going to treat them all like they're trapezoids. And the area of a trapezoid, in case we forgot it from the other day, it is 1/2 times the height times base 1 plus base 2. So if I'm doing this particular problem, I would have 1/2 times the height is actually the width right here, because what we kind of think of as the height vertically there, those are the bases because they're parallel to each other. So it's a little bit backwards. You could almost think of turning this on its side. This is your height, and then your bases, you have your B1 is over here, and your B2 over here. So the height of each one of these, what's that width there from 0 to pi over 6? It'd be pi over 6, so we'd have pi over 6. So 1/2 pi over 6, and then we would have, I'm going to do this, 0 plus f of pi over 6. And I'm going to use the calculator, so I'm not going to worry about that f of pi over 6 right now. And then I'd have another trapezoid, and it would be 1/2 times pi over 6 times, that's this one right here, so that would be f of pi over 6 plus f of pi over 3. And that would be the second one. Then I'd have 1/2 times pi over 6 times f of pi over 3 plus f of pi over 2. And then 1/2 times pi over 6. We'd have pi over 2 plus 2 pi over 3 plus 1/2 times pi over 6 f of 2 pi over 3 plus f of 5 pi over 6. And the last one, 1/2 times pi over 6 times f of 5 pi over 6 plus f of pi. And a lot of times when I do these, because they get so long and drawn out, I like to double check. I've got 1, 2, 3, 4, 5, 6 trapezoids there. Now, before I have to type all this into the calculator, because this right here is a pain to type in the calculator with all of those pi's and fractions and stuff like that, let's see if we can't make it just a little bit more simple. So, you probably got tired of me writing something over and over and over again, right? Because for every single one of these, I did this 1/2 times pi over 6. Okay. So all of those are the same. So we'll have 1/2 times pi over 6. I can factor that out. And so if I take all those and I pull them out front, we'll look at what we've got here. So if I pull all those out front, then I've got 0 plus f of pi over 6 plus f of pi over 6 plus f of pi over 3 plus f of pi over 3, right? So you'll notice that a lot of these are there twice. You've got the f of pi over 6, you got the f of pi over 2, you got the f of, I didn't put f's there, I should have. And then you got the 2 pi over 3, and then the 5 pi over 6. All the middle ones are there twice, right? Because everything in the middle here, it was a base of 2 separate trapezoids. So all of those middle sides got used twice. But the ends were only used once. So we can do this. F of 0 plus 2 times f of pi over 6 plus 2 times f of pi over 3 plus 2 times f of pi over 2 plus 2 times f of 2 pi over 3 plus 2 times f of 5 pi over 6 plus just f of pi. Now this is still a pain to type into the calculator, but it's a little bit less of a pain than what we had before. For this, yes. You're right. And in this particular case, you're right. That f of pi, we also could have just put a 0 right there. And since they're zeros and we don't want to have to type as much in the calculator, let's leave them off. That's a good idea. So in this particular case, you could. Now, if they were not 0, of course, you'd have to include them. And since those are, you're exactly right. Since those are both zeros, and that means we could take out a 2 out of this, which would cancel our 1/2. Oh, this Lily, you're making our lives so much easier here. So really, we've just got pi over 6 times all of these things right here. Now that worked out in this one because you had the zeros on the end right there. So let's put this in. I want to go to y equals, I'm going to put in our function, which is just sine of x. If you wanted, you could just do sine of all of these numbers yourself without doing without putting it in y1. It's really up to you. If you have a more complicated function, I would suggest putting it in y1. If it's something simple like x squared, you could do it like I did on the last problem. Sine x is not that bad. But I will use y1 this time. So we would have pi over 6 times, and then I'm going to do y1 of pi over 6 plus y1 of pi over 3 plus y1 of pi over 2 plus y1 of 2 pi over 3. Nope, forgot my plus on there. Plus y1 of 5 pi over 3. No, over 6. Okay, and I'm going to hit the green button before I hit enter because all those pi's will probably do something crazy. And so we get 1.9541. Hopefully that's right. Let me check. I'm going to check what the actual answer is. It'll be paper. Yeah. So you will not have, like, it's not like the state test where you got that little Desmos computer. I wish they would do that. Now, AP's been very slow to go to computer testing. I think maybe they do have computer testing for some. Probably one of the main reasons is because they're so international and probably don't have the same access to technology everywhere. But so they've been very slow to go. I don't know if they'll ever go, but they will. Everything's going to be on the computer one day. I'm worried that maybe, like, y'all might not even come to school anymore. You might just have a webcam, never leave the house. Yeah, it'd be so bad. Just completely not know how to operate in society with real people. Yeah, I hope it doesn't get to that, but I'm afraid that at least in the future there's going to be the option for that. And I'm not sure that'll be good for people. The actual answer for this is exactly 2. If you knew how to do it the other way. So it's a pretty close estimate. So I think we've done it correctly. I get a little nervous when I type all that stuff in and it's really long. Typically AP exam has gone with charts mostly on these, which we're going to do a few of here in a second. So it takes away some of that pressure of typing all that in, right? Okay. Yes. You've got pi over 6, pi over 3, pi over 2, 2 pi over 3, and 5 pi over 3. and you've got a pi over 6 out front. Mm-hmm. Yeah.
Reminder for Beta Club members to report to the auditorium at this time. Beta Club members report to the auditorium.
Is that everybody? Or? Yeah, I think they're just doing. I think awards for a convention are being announced. None of y'all went. You all right? Keep staying in here. Okay. I guess if anybody's in Beta Club and wants to go, you can. Okay. I'll be recording if you want to. Okay. All right. Okay, so what they have. Oh. Okay, so I actually probably should have put this rule right. Actually, no, this next one's midpoint, isn't it? No, it's trapezoid. Okay, so I actually meant to put this earlier, I think. So for midpoint rule, if you have equal subintervals, so if each one of your subintervals is the same, which maybe that's why. Okay. If each one of your subintervals is the same, you can kind of shortcut the trapezoidal rule just a little bit. And you can do that by doing delta x over 2. This is on the, not the next slide, but the next. Delta x over 2, which that delta x, that's the height of the trapezoids. And rather than saying 1/2 times the height, they have done height over 2, which is equivalent. So height of the trapezoid divided by 2. And then they just have this list where the first thing is their once. All the middle ones we multiply by 2. The last one we only do once. There. So it's sort of a shortcut that you can use for these. You do have to have equal subintervals. So if your table does not go up by consistent amounts, then you need to just kind of graph it if you need to and find the area of each trapezoid separately. So it only works for equal subintervals. But it does save a little bit of time for this. So if we look at example 3, it tells us the temperature in degrees Celsius of the water in a pond is a differentiable function W of time T. The table above shows, or it's below, actually, shows the water temperature as recorded every 3 days over a 15-day period. Approximate the average temperature in degrees Celsius. Oh, man. Yeah. I think so. Temperature in degrees Celsius of the water in a pond. Hold on. Now, this was an AP question I pretty much just copied. But I made these notes just special for you guys. I've not used them before, and I'm running into it. Oh, okay. I know what you need to do. Okay. This is actually a little bit ahead of what we're doing. Should we do it? It's very simple. But I don't think we're going to do it yet. I think we've got enough other examples. We're going to skip that one. I did not read the question carefully enough. Let's go to 4. Because 4 is going to be pretty much the same. Just a little bit different. So 4 says the table below shows the speed of a car in feet per second over 1 minute. Use a trapezoidal approximation with 6 subintervals to estimate the total distance that the car traveled over the minutes shown in the table. So right here, if we were to graph this, which I'm not going to, I'm going to use my trapezoidal rule to save me a little bit of time. But if we were to graph, this bottom would be seconds, and this side would be feet per second. And so if I find the area, length times width, feet per second times second, that would give me the feet that the car has traveled. So if we found the area underneath the curve for this, it would give us the distance that the car has traveled, or at least the estimate for it. So If I'm going to use that trapezoidal rule for this, rather than trying to do each trapezoid separately, what is the delta x? What is the height, or I want to call it width because it looks like width, of each trapezoid? What? Okay, so I see what you're saying. So each one has a width of 10, but then you have to divide it by 2. Is that right? What you're thinking? Okay, so you will have 10 divided by 2, or it's like 1/2 times the height, which is 10, so we get 5 there. And then we are using y values here, because we're finding f of 0, and f of 10, and f of 20. We are not finding, in fact, just for clarity, I'm going to write this out. We're doing f of 0 plus 2 times f of 10. You do not have to write this on every problem, but just for clarity, to make sure everybody knows exactly what we're doing here. In notes, we'd have 20 2f of 30 plus 2f of 40 plus 2f of 50, and then 60, that very last one, we would just count it once, like this. And so for this, a lot of these problems, they give to you a lot on the AP exam. Rather than giving you the equation that takes forever to type in and you might mess up, sort of like the last one, they usually give you a table if they're wanting you to do this. And when we do the table, sometimes they might give you a graph instead, but they don't usually give you the equation of the function. So when we do the table, we're going to use that first number once, so we'll have 0 plus 2 times 15 plus 2 times 24 plus 2 times 31 plus 2 times 45 plus 2 times 52 plus 65 here. And then sometimes this also allows them to give you these that are calculator inactive sometimes. Usually if it had these numbers, they'd give you the calculator. But sometimes they might give very small numbers where you could do it calculator inactive. But if we just check here, we would have 5 times 30 plus 48 plus 62 plus 90 plus 104 plus 65. And we should get 1,995 feet. I think, unless I type something wrong. You might want to double check me on that. But this is much easier to feel pretty confident that you've typed it in right than the last problem. So this is usually what you see on the actual AP exam. Now, keep in mind again, this only works if you have equal subintervals. If your subintervals are not equal, so if it went from 0 to 20 and then 20 to 30 and then 30 to 35 or something like that, you would have to do each trapezoid separately. Kind of like we did a couple of days ago when we started all of this. You just draw it out, find the area of each trapezoid. It's a little time consuming, but it's just basically area of the trapezoid, so it's not too terrible. Okay, questions? Okay, let's look at what this looks like when we do it with midpoints. Okay, so this gives us the graph of the velocity in feet per second of a car traveling on a straight road. For 0 to 50 is shown above. A table of values for v of t at 5 seconds, 5-second intervals of time is shown to the right of the graph. Approximate, and I copied in pieces, but approximate the area under the curve v of t on the interval with a Riemann sum using the midpoints of 5 subintervals of equal length using correct units. Explain the meaning of this interval. Okay, So they have given us, we have equal intervals here. They want us to do a midpoint Riemann sum. We want 5 subintervals of equal length. So if we're going from 0 to 50 and we're splitting that into 5 subintervals, that means right here at 10, 20, 30, 40, and 50 are our places where we have our rectangles. But we are using the midpoint. Now, you are not trying to find, like add things together, divide by 2 to find the midpoint. The midpoint between 0 and 10 is 5, so use the value they gave you at 5. So it would look like this on the graph. And then for 15, that's halfway between 10 and 20, so you would use that y value for 15. And then for 20 to 30, you would use this one. 30 to 40 would be this one, and that last one would be right here. So we're using f of 5, f of 15, f of 25, f of 35, and f of 45. Now, I think it's very helpful that they give you the graph here. That really helps me picture what's happening. Sometimes they'll give this to you with just the table, and students struggle with that when they give you just the table. My suggestion to you is you can always just sketch yourself a rough draft, or, you know, even if the numbers are hard to draft, get just a rough look at what it looks like to draw it out, and that'll help sometimes. So the width of each one of these rectangles is 10, and then we would have f of 5 plus f of 15 plus f of 25 plus f of 35 plus f of 45. And always make sure if it says 5 subintervals, you should have 1, 2, 3, 4, 5 things here if you're doing a Riemann sum, left, right, or midpoint. Now, trapezoids are a little bit different. You count all the middle ones. You use every interval for it, but you count the first and last just one time. All right, so in this case, f of 5, it tells us is 12, and f of 15 is 30, and f of 25 is 70, and f of 35 is 81, and f of 45 is 60. And so 12 plus 30 plus 70 plus 81 plus 60 would be 226. So you got 10 times 226, which would give you 2,260. This one is also feet. Yes. This one is not trapezoids. So when you're finding, like if you have a trapezoid like the last one, for each one of those you're doing 1/2 times the height times base 1 plus base 2. Which means since you do that, whenever you do that each time, like we did on this one right here, like the 1/2 times the width or the height will be there. And then so in the first trapezoid, you got the first base and the second base. Well, then in the next one, you got the second base and the third base. So it's repeated there. But that's for trapezoids. For the midpoint, you're just doing rectangles. And rectangles is just base times height. And so the base is 10 for each one of these. The height is just the y value of that midpoint for those. That's a good question, though. Yes? Oh, good gracious. You're right. Let's try that again. Let's go up here and see if we can't fix that. Okay, never mind. 253